this algorithm run. Okay, and we can kind of compare algorithms and say, okay, this one's slow, this one's fast, this one's medium, right? And we have ways of doing this, and so that's what we'll talk about and sprinkle in today's lecture. Make sense? All right. So it's nice to sort arrays or other data structures. So all of my pseudocode and examples will deal with sorting an array because array holds a bunch of data. There are other data structures that hold data, and so you can sort anything. But our lecture today will really be about how to sort arrays. But really, any data structure that holds a bunch of data, you could sort in different ways. There's lots of different algorithms, but they all solve the same problem. Right? The problem is I have a bunch of data, I want to sort it. That's the problem. Right? Bubble sort, selection sort, insertion sort, shell sort, merge sort, quick sort, heap sort, so on and so forth. There's a cocktail shaker sort. That one's kind of fun. It's really bad, but it's fun to watch visually. They all solve the problem, right? The problem is I want to sort my data. I didn't make this up. It's a real sort. Right? Usually they're simple to write or they're efficient, but usually they're not both. So we're going to start with the, lucky for you, the easy to write, but really inefficient algorithms. Okay, so that's where we're going to start from. And then eventually we'll get slightly more efficient, although we won't get to the really efficient ones, as far as making you write them. Sound good? All right, you want to look at bubble sort? Say yes. Yes, I do. Yeah. Maybe. All right, so in the context of an array of integers, right, let's talk about the steps to do a bubble sort. We will compare the first two elements of the array, so element 0 and element 1. Okay, we will compare them. Are we good with that? Are we good? When I say compare, in your mind, you think of what? How do you do comparisons in code? Right, greater than, less than, right, inside of some if statement, right? If they are out of order, I'm going to swap them, right? So if I had two numbers, right, let's not even say an array, and let's say we're going from smallest to largest, right? If I had those two, I compare them. If they're out of order, what am I going to do? Swap them, right? How many times have you written the swap algorithm in the last 2 semesters? The last 3 classes? A lot, right? So hopefully you can write that. Right? And then you keep doing that for each pair until you hit the end. So as you have more values, you keep, okay, 9 and 10 swapped, 10 to the next one, right? Check them, and then if they're out of order, what do? Swap them, and then the next one, and you possibly swap them. And you keep doing that, okay? So we go through the array one time, swapping every other one if, right, they're out of order. Does that make sense so far? And so at this point, after I've gone through my array one time, guaranteed the largest value is at the end of the array. Does that make sense? Because if it was the smallest, if the largest value was at the beginning of the array, it would swap every time to get to the end. So one pass, we're going to call them passes, so one pass through the array, the largest value has what? Bubbled to the end, or to the top. I'm going to go with the bubble. Right? That's where the name comes from. You're bubbling the largest value to the top, right, to the end every single time. But that's only one time through the array, and I guaranteed that one value is exactly where it's supposed to be. Does that make sense? So then what do I need to do? Go through it again. Start at the beginning again, and go not to the end this time, but go to the end minus 1, because the last value is where I want it to be. So go to the end minus 1 and do the same thing and swap. At the end of 2 passes, guaranteed the last 2 values are what? The 2 largest values. And I just start at the beginning and what? Do it again. And do it again and do it again. Right? This is very inefficient. All right, how many times do you gotta do it? You gotta do it a lot. Okay. You ready for my awesome array? So any sorting algorithm that you're going to throw at this array is going to sort it, right? Where 7's at the beginning, and then 9 and 13, and right, so on and so forth. So let's look at this. Bubble sort will look at the first value and compare it to the next, and if it's in the wrong order, right, it'll swap it. So first pass, right, 24 and 13, these are the 2 values to compare, right? And what does the algorithm say? It says Wrong order. So what do? Swap. So they get swapped, right? And then the next two. My animations are all wrong. 24 and 9. Oh, I guess it's not wrong. It's just being weird. So, right? 13 and 24 were in the wrong order, so we swap them. We move to the next two. 24 and 9 are what? In the wrong order, so we swap them, right? See, it's kind of working, right? And then we continue to do that until everything's sorted. So 24 compares to 64, and what do? Leave them, right? So you don't always swap, right? And then 64 and 7, and what do? Swap. And then 64 and 23, what do? Swap. 64 and 34, right? 64 and 47, swap. You notice that once you find the largest value, it's going to get swapped all the way to the end, right? And sometimes swaps are efficient, and sometimes swaps are inefficient, depending on the data structure that you use. Make sense a little bit? You guys want to visualize it a little bit? One way to visualize bubble sort is like this, right? Where the top right are the largest values, and the bottom left are the smallest values, right? And the largest values slowly bubble to the top as things swap. They kind of look like ants that are all getting in line, right? How many times can you watch it? It's just a loop. It's not going to change. You ever watch loop things and thinking, oh, maybe on the 100th time it'll be a little bit different? It won't be. Let me show you another thing. They changed the URL of the website. Here we go. All right. Remember I said there were a bunch of algorithms: insertion, selection, bubble, shell. Those are the four that we'll do. Right? There's a merge, a heap, a quick three. So we're gonna go into bubble. Maybe we make them a little bit bigger. Right. Okay, yeah, so what do those mean, right? We see random, nearly sorted, reversed, few, unique.
How sorted the data set?
Right, how sorted the data set already is. Okay? We normally think of data sets as being random, right? But there's a lot of data sets that are like almost sorted, but not fully sorted. There are data sets sometimes that are pretty much backwards. And there are data sets where there are a bunch of the same values in the data set. And what happens is that different algorithms might be better at random, but worse at reversed. Or might be better at few unique and worse at nearly sorted. Right? And so we have different algorithms to attack different problems. Ready to play all? Right. So this is them, they're bubbling to the, you notice they're bubbling to the
lowest one.
Right, yeah, lowest. So it's just a reverse bubble. Which one was the fastest?
Nearly sorted?
Nearly sorted, right? Because, right? They didn't have much to do. What? Yeah, right? It's like, oh, sweet, it's good. Do you want to see it one more time?
You watched this the whole class?
Yeah. I know. Now that I showed you these, I'm going to lose you. You're going to just Google them and YouTube them and do all sorts of stuff.
What's that URL?
Can't tell. Oh, do we like cookies? Yeah, we got it. Thank you. We like cookies. Look, there's the pseudocode. Although that's not my pseudocode, so don't steal theirs. The caveat on the nearly sorted is that it worked because they were still kind of in the right order. But if you had the largest value here, right at the top, right, it would only, as I move things up, it would only move down one every time. And so it would go from being like super fast to being just as slow as any other, right? By just having one thing in the wrong spot. So bubble's not necessarily great. I think you're kind of getting it. Look, this was still going on. All right, let's talk about the pseudocode, right? If I want to get to every value in an array, what do I need?
For loop.
A loop, right? Good, for loop. Now, we said that that was only past what?
Once.
1. So if I want to go to the end and then the end again and the end again, what do I need? Another loop, right? So 2 loops, right, together. Notice this loop says what? For I equals n minus 1 to 1. Okay, pay attention. That's not the type of loop that we normally write. We normally start at 0 and count which way? Up. And this loop starts at what? Some number at the end. N is the size of my array and counts which way? Down. Okay, let's talk about why we would do that. Right? Here's my array. Right? It doesn't really matter how many values I have. Right? And basically that first loop says that we're going to go, right? I is going to start out here. Right? And then I is going to move where? To here. Does that make sense? In essence, what am I doing? I'm kind of making my array smaller, right? Because I is moving down every loop, right? And so I is the full size of my array. Now I is 1 less, and 1 less, and 1 less. And why would I do that? What does bubble sort do? One thing to where it needs to be. And when it gets to where it needs to be, which the first time it's going to be at the end, do I need to sort that next time?
No.
No, so I want to move which way for the size of my array? This way, right? Because I can ignore this value, right? So I is making what I'm trying to sort smaller because every time I go through and sort, I've gotten one value where I need it to be. Does that make sense? Questions on that? So that's making it smaller, that's my outside loop. But my inside loop needs to say, okay, for however many values I want to compare and swap, right, I need to start at the beginning and go to the end of the array. And the end of the array really being I. Does that make sense? So my next for loop starts not at the end, but J starts at where? 0. And I go to where? I minus 1. And the reason I go minus 1 is because when I swap or when I compare, I'm looking at where I am and the next one, right? And if I didn't say minus 1, I would look at the last value in the array and the what? Right, off the cliff. You don't want to compare off the cliff. You don't want to sort, right, garbage values into your array. That doesn't sound like a good idea. And then, right, if my array at J is bigger than the next spot, meaning if the value at the beginning of my array is larger than the next value, then what am I going to perform? A swap. Okay. So let's do this on a small array. So we have 7, 2, 1, 5, and 3. Okay. N is what? Good. Which means I is
4? Yeah.
right? It says I equals n minus 1. All right. We're going to go all the way down to where? To when I is 1. When I becomes 0, we're done, right? Okay. Notice, right, then the first line of that for loop is another for loop, right? Where we create a J, and we started at 0, okay? And we go to where? I minus 1, which means we go to where? 3. Right? Let's do our replacement. Okay, so if A of J is bigger than A of J plus 1, well, J is 0, right? So is my array at 0 bigger than my array at 1? Yes, right? So that value is true. So what do? Swap. Okay, that ends that iteration of the for loop. So what happens?
Goes back to the top, right?
Go back to the top, and the top for us would be this for loop right here. Oh, you can't even see my mouse. Oh, here we go. This for loop right here, right? Because we're on the inside for loop. So J gets incremented. Notice the first for loop is a decrement, right? You should say I minus minus. And the J loop is an increment. You should say J plus plus. Sometimes students screw that up and then you get an infinite loop. That kind of sense. Right? So J becomes 1. Is my array at 1 bigger than my array at 2? Yes. And so what do?
Swap.
Swap. We make a weird looking 7. Why not? Okay. That iteration of the loop ends. J becomes what? 2. Is my array at 2 bigger than my array at 3? So what do? Swap. It kind of sucks when the largest value is at the beginning, right? Because you do a lot of swaps. Okay. J becomes what?
3.
3. Notice it says J equals 0, 2, I minus 1. I was 4. 4 minus 1 is 3. Okay. When it says 2, right, that means like less than or equal, right? Because I'm going to go to that value. So I still need to do the 3, right? Which makes sense because did 7 get all the way to the end yet? No. So is my array at 3, is it bigger than my array at 3 plus 1? Yes. So what do?
Swap.
Swap it. So 7 goes here and a what? A 3 goes there. Okay? Then J becomes what?
4.
4. And I was only supposed to go to where? 3. So what happens to the for loop? It ends. Right? So in essence, all of this actually goes away. Right? But my for loop was inside another what?
Another
For loop. So now I go to that condition. Right? I'm going from right n minus 1 down to 1. So 4 becomes what?
3.
3. Yay! And I haven't made it to 1 yet. So what do I have to create now? A J. J starts at 0.
Oh, jeez.
We do it all over again, right? Is my array at 0 bigger than my array at 1?
Yep.
Yeah, so what do?
Swap.
Swap. Things are starting to look pretty good. Right, J becomes what?
1.
1. Is my array at 1 bigger than my array at 2?
No.
No, so do I do anything?
No.
No, besides just increment 1 to what? To 2? Is my array at 2 bigger than my array at 3? Yes, so what do? Swap. Right? Remember, that loop only goes to what? I minus 1. Well, I is 3. I minus 1 would be what? 2. Right? So I've now done my second pass. Does that make sense? I've done my second pass. Okay. Before we move on, right, what do we notice about my array?
It's already in order.
It's in order. What do we know about the algorithm? So it's going to keep going. It doesn't know we've made it all the way in order, right? So now we're just going to do a bunch of comparison stuff. So J loop ends, I becomes what? 2, which means J starts always at 0. Is 0 bigger than 1? Is A at 0 bigger than A at 1? No, so I don't swap. 0 becomes what? 1. Is my array at 1 bigger than my array at 2? No. Right? So it becomes what? 2. Well, my loop ends. Right? What happens to I? It becomes
1.
1. Because it says 2, 1. So that includes 1. Right? 2, 1 would be what? Either greater than or equal to 1, or you could also just say greater than 0, depending on how you want to write it. So that's that. J starts at
0.
0. Is my array at 0 bigger than my array at 1?
Nope.
No. J becomes 1. Well, I've gone as far as I needed to go. So my J loop ends. This technically becomes 0. And then my I loop ends. And at the very end of all of that erasing and swapping, what happened? Is it sorted?
Yeah.
Yeah. So did it work?
Yeah.
Yeah. Right? And some amount of swaps, right? And some amount of comparisons. But eventually we got there. On a really what? Small array.
It was like 30.
Right? Exactly. Right? Quite a bit on a really small array, right? So do we think this algorithm is fast or slow? Slow? And we're not basing that on how fast I can write on the board, right? But how many passes I have to do and how many comparisons and swaps I have to do. Or I could have done it really fast. I put a lot of O's for emphasis. How many comparisons the first time? How many times do I compare when I pass, when I make a pass? How many comparisons? Okay, well, let's look. The first time I went, did I compare these two? So that's 1. Did I compare these two? That's 2. I compared these two, that's 3. And these two, that's 4. So the first time I went, how many comparisons did I have? 4. How big was my array?
5.
5. So mathematically, how would we write that? If I tried to expand it to any size array?
-1.
N minus 1, good, right? N minus 1, right? I do N minus 1 comparisons the first time. The second time, how many comparisons do I do? N minus 2. The third time, how many do I do? N minus 3. Anyone good at math? Nobody's good at math.
Yeah, she's just like.
Right? So you get to an arithmetic series, right? Because you're saying N minus 1 and N minus 2, right? You got to get all the way down. So the arithmetic series comes down to this. N times N minus 1 over 2. Right? Which becomes N squared over 2 minus N over 2. Okay, so we do N squared minus or over 2 comparisons, and we subtract N over 2 comparisons. Okay? N squared is exponential. Everyone good with that? N would be what? No. What?
Size?
No. Well, it is the size of the array, but if I'm looking at N squared versus N, we'd say N squared is exponential, we say N is linear. Right? Because as N gets bigger, right, it just gets 1 bigger every time. Right? Whereas, right, we get our parabola if we do our exponential. Does that make sense? So which one gets bigger between those two? The N squared over 2 or the N over 2? N squared, right? So as N gets larger, N squared basically dominates N. Does that make sense? When it's small, does it dominate? Not really. But when we talk about 100 squared versus 100, well, 100 squared is, it's some more zeros. What do we have? 100,000 or something like that versus 100. Right? It doesn't take much for the exponential thing to majorly dominate the linear thing. Does that make sense? Am I kind of tracking? Right? So we say that N squared dominates. So for large values of N squared dominates the N value. So even though we're subtracting N over 2, and even though we're dividing by 2, it doesn't really matter. Because N squared, the exponential part, dominates every other part of the equation. All right? Which means that we say the efficiency of the algorithm, because that's the thing that dominates, the efficiency of the algorithm is what? N squared, so it's exponential. Right? So we say big O of N squared. All right? Big O notation of N squared. That's the efficiency of the algorithm. Okay? Meaning it's slow because it's taking exponential time. As I add more values to whatever I'm sorting, it gets exponentially longer to do. Does that make sense? Am I kind of tracking? So, bubble sort slow. Yay, N squared. Not so good. Okay. How can I make bubble sort more efficient? Well, that's selection sort, which is what we're going to talk about here in a minute. And we'll see if it's more efficient or not. How else can we make bubble sort? Keeping the same sorting algorithm that we have. What do you think? Make it so it knows it's done, right? At some point when we were doing this, everything was in order, right? And in fact, everything could be in order from the get-go. You could get lucky, right? But a regular bubble sort would still compare. Compare, nope, don't swap. Compare, don't swap. Compare, don't swap. Compare, and compare. I think I did that all in order, right? It's one less every single time. One less compare. But if I can figure out, hey, I'm done, right, after just one pass, if everything's where it's supposed to be and I didn't, right, have to change anything, then I know I'm done, okay? So I'm trying to lead you to that, right? To make it more efficient, we have to say I'm done. And how do I know I'm done? When the swap doesn't do anything. So when you have all your comparisons and you never swap, right? If I look through my whole array and I never make a swap, then everything must be what? In order. Make sense? So we just did a basic if statement. All right. So the efficiency of optimized bubble store is still n squared, right? Overall average case, because values are randomized or whatever, it still takes n squared amount of time. But notice here I'm going to throw in best case. Best case is linear, right? Because if everything's already sorted, right, I go through the array how many times? Once, and it's sorted, I'm done, right? N is the best you can get, right? Because to see if something's sorted, you at least have to look at every value how many times? Once. So N is the best you can be. Bubble sort, optimized bubble sort can get you there. But everything has to be sorted. Remember when we said if one value is in the total opposite place of where it's supposed to be, then it's not good. This is the same algorithm. I have my I for loop, I have my J for loop, but I've added a flag, right? Some Boolean, right? And every time I pass through the array, I set that flag to false, right? I have not as yet swapped any values. Does that make sense? And then I have a simple if statement. If A of J is greater than A of J plus 1, right? That's our check. If that's true, we swap. And we also set our flag to true, okay? Because I swapped. Then, when I'm done with my J loop, notice the indentation, right? So this is not in that for loop, right? It's outside of it. When I'm done with the for loop, I check if swapped is false, then I break out of the loop. Meaning if I went through the entire array and I never swapped, then the flag stayed false, and so everything's sorted. No. Yeah. And in fact, to pass all the algorithmic stuff, the algorithmic test in your lab, you'll need to use my pseudocode. This is pseudocode. When I compare two things, what do I do in C++? How many equal signs? 2. So don't just put in 1, right? We don't do 1 for a comparison, right? We don't do indentation, right? Pseudocode does, Python does. What do we use? Right, 2 spaces with some curly braces, right? So you're going to need it, right? You have to translate the pseudocode into C++.
You can use the swaps inside of an if print, as a, and then that determines only if it completes or not.
Yeah. And then the other thing is that swap is not a function, right? You have C++, so your lab, you'll write the swap function and then call it. All right? I'm not going to go through it. It's pretty much the same. Let's get to our other one. All right, so the other one we have is selection sort. Thomas already said what it's going to be. Let's find a value and then put it where it's supposed to go. All right, so that's selection sort. So selection sort takes either the min algorithm, right, find the smallest value in an array, or the max algorithm, find the largest value in the array, and combines that with sorting to get everything where it needs to go. All right. Just because mine might be like find the smallest, you might see other selection sorts that say find the largest. So step 1, go through the array and find the smallest element. Right? Go through the array and find the smallest element. Guess what? When you find the smallest element in the array, where's it supposed to go? At the beginning. Right? So once you find it, you know where it goes. So then you swap it there. So you take it from wherever it is and you put it at the very beginning. You take whatever is at the very beginning and put it back to where you are. Does that make sense? And then I've done that for the first one, so now I need to move to the second one, go all the way up, and swap into the second place, and then start at the third spot, go all the way up, swap it into the third space, fourth, right, as many as I need to do. All right, so here's my lovely values. All right, so let's look at this. So we start at the beginning. You'll notice this time I have an array, but then I also have an index. The index being what? No, this one's not going to be for passes. This one's going to be for what is the smallest value, because that can change. You'll notice though you always started at 0 because if I've only looked at one value in my array, it is the what?
Lowest.
Lowest value, right? It's the smallest value, right?
Unless you compare it.
Well, but I've only looked at one, right? That's why I started at 0. So I start at the first value, it's the smallest. So the index is 0. All right, so now I look at the next one. I look at 17. I compare 17 to my array at the smallest value, right? It was 0. So I look at my array at 0, right, which is 34, compare it to 17, right? Is 17 smaller than 34? Yes. I do not perform a swap, though. That's bubble. Right here, I just changed my indice from 0 to what?
To 1.
Not 17 to 1. We're just going to store the index, not the value. Because I already have the value in the array. So I just need the index, basically, right? Where is it located? Does that make sense? And then I look at 23. I compare 23 to my array at the smallest value, right? Is my array the smallest value is 17, right? It's smaller than 23, right? So this stays as what? As 1, right? And then I compare 35 to 17, and it stays. And then I compare 45 to 17, and it what? Stays. I compare 9 to 17. That should have been a 1. That's a typo, right? And is 9 smaller than 17? Yes. So that value, which was 1, becomes 0, 1, 2, 3, 4, 5. Does that make sense? And then this one, which was 5, right? I should probably fix my slides, right? I compare 1 to my array at 5, which is 9. Is 1 smaller than 9? Yeah, so this value becomes what? 6. So 1 passed through my array, right? And basically with a find min algorithm, and I found the smallest value in the array. Agreed? What does it say we do now with that value? We put it at the very beginning, okay? Now, to do that, we just swap the first value to where that value is. Okay, we're going to get to data structures soon. Putting a value at the very beginning of the array is not easy because all the other values have to what? Move down. So that takes a lot more work, so we're not going to move them down, we're just going to literally swap it. And so in selection sort, your array might get less sorted before it gets more sorted because you're just swapping values right all over the place. So we have that, so we swap. 1 is now sorted, that's why I made it red. Where did 34 go? To the end. All right, and now I basically ignore 1 and I find the smallest value in my 17 to 34 array. Does that make sense? So, right, we initialize it to, right, 1 because I already did 0, so I want to start at 1. So now 17 is the smallest value in my array, right? And then I keep doing that, right? Okay, is 23 less than my array at 1? No. Is 35 less than my array at 1? 45. Is 9? Yes, so my smallest value is not at location 1, it's now at location 5. Is 34 less than my array at 5? No. So then 9 swaps with 17. So 17 would come over here, 9 would come over here, and 1 and 9 would be my sorted array, and 23 through 34 is now my unsorted array. Does that make sense? So every time I find the smallest value and put it into the next spot. Find the smallest value, put it in the next spot. And if I do that enough times, what happens? My array becomes sorted. This one looks more like popcorn, which makes sense, right? Selection sort is called a not stable algorithm.
Sounds slow.
Bubble sort is stable, meaning that the values are always still kind of in the right order. Right? Selection though is taking values, right, and jumping them around. And what will happen is that if you have two values that are equal, right, whatever you define as equal, in a stable sort, they'll still stay in the same order. So if this value and this value, if they were equal, this one will always stay smaller than this one. And in selection sort, because it's unstable, because things are jumping, it could be that this value, which even though they're equal, this one was smaller, right, will end up being bigger. Okay? Does that matter for integers? No. Does it matter for like objects where what you're comparing for smaller and larger is one thing, but then they also have other data associated with them? Yeah, it does, right? So we have stable algorithms and unstable algorithms. You said it seems slower?
Yeah, it looks slower.
All right. Well, it's going to be slower for me to draw on the board. So it's got a little bit more to it. It still has a swap in it, so we'll talk about what the algorithm's doing. But this one's a little bit different because the first time I sort everything, everyone see that? And then what? My array to sort gets smaller every time. Does that make sense? In bubble sort, it was large and it got one smaller from the largest side because we bubbled values to the top. Here we find the smallest, so we move them to the front. And so I need to sort this much of the array, and now I need to sort this much, and now this much, and now this much, and now this much. Does that make sense? Which is why my for loop now starts low, I equals 0, and goes up to what? N minus 1. Right? As does my J loop. So let's look at what we can do with this. 7, 2, 1, 5, 3. N is 5. Everyone go with that? I starts at what?
And then this one.
Well, no, not this time.
Oh,
It starts at 0 and it goes to N minus 1. So it's going to go all the way up to 4. Notice we have a new value, smallest. Right? Smallest starts at what? Notice it starts at I. Right? Which at the very beginning, I is what? 0. But then it's what? 1, and then it's 2, right? Because once you find the smallest value, you put it at the front, you want to take the next spot and get the smallest value there. And then you want to take the next spot and get the value there. We tracking on that? So smallest becomes I. I here was what? 0. And then I have a new loop, which is J. J starts at what? I plus 1. Okay, so J starts at what? 1. Okay, that's because I already know where the smallest value is, right? I've already looked at this one theoretically, right? And so I want to compare everything to that, so I want to start one farther down. Right? If I say 7 is the smallest, right? Because we said smallest is 0, I don't need to compare 7 to itself. Agreed? I need to start where? At the next spot, which is why J starts one farther, right? J starts one farther than the smallest thing. If A of J is less than A of smallest, A of J is location 1, A of smallest is location what? 0, right? Is A of J smaller than A of smallest?
Yes.
Yes. Okay. No, we do not do a swap. What do? Smallest value becomes what? J's value, because we said A of J was smaller than A of smallest, right? That's the find-min algorithm, right? Isn't that the find-min algorithm? Start with a value, compare the values to it. If they're smaller, then that becomes the smallest value. So smallest becomes what? 1? Okay. This is outside that for loop, right? Because they're at the same indentation. So I made it to the end of this iteration of the for loop, so I go back to here, right? What happens to J? It goes up by 1. And then we compare again. Is my array at location 2, is it smaller than my array at smallest? Is 1 smaller than 2? Yes. So then smallest becomes J again, so smallest becomes what? 2. I continue on. Is my array at 3 smaller than my array at smallest? And the answer is no. So do I do anything here?
Nope.
No. Then 3 becomes 4. Is my array at 4, so is 3 smaller than my array at smallest? No. All right. So my J loop ends. Okay. The J loop, which is this 3 lines of code, ends. And then if smallest is not equal to I, Is smallest equal to I?
Nope.
Smallest is 2, I is
0.
0. Okay, so then what do we perform?
Swap.
Swap. A at I, which is 0, swaps with A at smallest, which is 2. So 1 goes here, and 7 goes here. I found the smallest value, and I put it at the beginning. Right? But that was first pass, right? So now I has to become what? 1. Smallest becomes I, which is also 1. Right? J starts at I plus 1, which is 2. Right? Is my array at 2 smaller than my array at smallest? Is 7 smaller than 2? No. So J now becomes 3. Is my array at 3, which is 5, is that smaller than my array at smallest, which is 2? No. Right? So 3 becomes what? 4. Is my array at 4 smaller than my array at smallest? No. Right? Which you guys already knew. Right? You knew 2 was where it was supposed to be, because it's a smaller one. Okay? Now let's talk about why we have this if statement. If smallest is not equal to I, well, smallest is what? 1, and I is 1. Are they equal?
Mm-hmm.
Yeah, so do I perform a swap?
No.
No. Because why would I swap 2 with itself? Right? Agreed? So if it's already where it's supposed to be, don't do a swap. All right, so that ends that iteration of the J loop. Right? So now I becomes 2, which means smallest also becomes
2.
And J becomes 2 plus 1, which is
3.
3. Is my array at 3 smaller than my array at smallest?
Yes.
Yes. So smallest becomes J, which is 3. J becomes 4. Is my array at 4 smaller than my array at smallest? The answer is yes. So smallest becomes what? 4. J loop ends. Right? And then if I and smallest don't equal each other, which they don't, we perform a swap. So my array at I, which is 2, swaps with my array at 4. So 2 and 4 swap. So 7 comes here, and what?
3 goes there.
3 goes there. Okay? Then I becomes what?
3.
3. Which means smallest also becomes
3.
3, which means J becomes
4.
4. Is my array at 4 smaller than my array at 3? No. So that ends my J loop. Isn't that crazy? End of J loop. Right? Does I equal smallest?
Mm-hmm.
So do I perform a swap?
No.
No. And I don't go any farther because now that I did that, the last one's where it's supposed to be. So I've taken care of all of the other ones. So I don't need an extra loop. Does that make sense? Do you think this one's fast or slow? It feels slow.
Yeah.
Well, it also, right, we're not going to make you do the math this time, but it also comes out to O of n squared. So it's slow, but bubble sort's slow as well. Okay. Selection sort is kind of like, it doesn't matter what your data looks like, whether it's reverse sorted, nearly sorted, unique values. It just does the same thing for everything. All right, so it's basically just as crappy for any data set, okay? Whereas bubble sort can be efficient for almost sorted data sets, but then inefficient for almost every other. But selection sort is easy to understand because we've done find them a lot, right? And so we just take that and just do it over and over and over again to sort more. Let's visualize that. Hey, look, I'm done. Am I done on time too? It's so weird. All right, so that's bubble. Go back to the algorithm. What are we doing? We're doing selection stuff, right? This is me wasting your life. What do you see? All the data sets, all the same amount of time, right? Because the nature of it, where it's finding the smalls and just swapping it with the front, means that the rest of your array stays jumble sorted, right? And so it has to, no matter what the data, it has to keep going through everything every time in order to get it where it needs to be. They'll never get to an almost sorted kind of way. I think we might be able to see the two together. Let's see. All right, we're gonna do insertion. Don't look at that one, but you can look at selection and bubble together and see, right, how they go. So bubble's done with one of them, right? So selection's just slow, right? Bubble's a little faster. Did anyone look at insertion even though I told you not to look at it? Raise your hand, admit to it. Anybody? Right? Did it get done basically before all the other ones? Yeah. So it's a little bit more efficient. Although it's slow on reverse, but we're gonna talk about that on Monday.
What's the algorithm that keeps having the list?
That's merge sort. Because you break it down into two lists and then you merge them together. And you keep doing that recursively until you're done.
How fast is that one?
Faster.
Oh. Oh shit.
Oh, jeez. Quick?
Hey, this is kind of fun. Here's the 4 fast ones: merge, heap, quick, and quick 3. I'm going to teach you these 4 slow ones. Local and shell. But you should be thankful because remember I said they're either fast or they're easy to write. And I'm giving you easy to write but slow, which I think you're going to be happy about. Yes. All right, so I'm going to go over those 2 next time. We're going to watch some YouTube stuff with Cocktail Shaker and all sorts of fun ones. I can't remember the name of it, but there's one. The sort is you just pick 2 random indices in the array. So just pick 2 random spots and swap them and then check if it's sorted. And then pick 2 other random ones and swap them and see if it's sorted. That one has a really bad big O notation, right? Because eventually it'll work, right? Like if you take a deck of cards and you shuffle it enough times, maybe eventually they'll all be in order, right? But you just don't know how long it's going to take. So.
Competition where you have to program the slowest algorithm.
Oh yeah, right.
And you basically, I think you just do that. You just didn't do anything. You just keep checking it to see if it was sorted.
Right. Is it sorted? Is it sorted? No. Yeah. Anytime that you get 4 loops inside of 4 loops inside of 4 loops, right, your data complexity is crazy. Your time complexity. Okay, so I did not give you any C++ code. Agreed?
Mm-hmm.
Right? But what did I give you? I give you pseudocodes. Right? So start with this one, and I'll leave it on the board. Start with this one, right? Which that's the easiest one, the bubble sort, right? Start with that, and then work on the next one, which is improved optimized bubble sort, and then do selection. So those are the 3 that you need to do today. Make sense? But I promised you I'd talk about the assignment too. So let's talk about that. Because you should by tomorrow be done with the first part. Yeah, you heard that right. You should be done with the first part. Even though I haven't even told you about it.
We should be starting it today.
Yes. I even extended it to be due slightly later. This assignment?
Next week.
Yeah, or the week after. I think the week after.
November 7th.
Yeah. It was going to be due on Halloween night. That's why.
Lab 14?
No, the assignment. The big scary assignment.
That's why I was doing Halloween.
How would you make the UI? Or like, what is that?
Yeah, we can talk about it.
Just an interface? Or?
Yeah, the UI, you're like, you always just give us unit tests. I have never had to deal with user interaction, but you're gonna have to deal with user
Is
interaction.
it like kind of like you ask the user, oh, what do you want to do? Oh, you want to do that? Cool.
Remember when you wrote programs like that?
Yeah.
Yeah, we're gonna do that again. All right. Okay, I'm gonna try to succinctly talk about what this assignment's trying to do. So you're gonna make a application that's called a to-do list. There's an application where a user can come in and create like to-do items, like, don't do assignment on the last day, right? Insert it into my program, and that kind of stuff. That should be the first thing that you put. So you're going to be able to add, edit, and delete to-do items from a to-do list. And so it's all class-based, so we're going to have a class to-do item. We're going to have a class to-do list. And then there's going to be a UI that allows the user to actually interact with those things. And so there'll be a class called to-do UI. So you end up with three classes, to an H and a CPP for each class. So that's 6 files, plus a what? Plus a driver, right? So you're going to end up with how many files? 7. Normally we work with how many files? 1. So you're going to have 7 files that all go together to make an application. Hey, it's like something real. In the UI, you'll create one to-do list. And the to-do list deals with the to-do item, so the UI doesn't care about the to-do item. Yes. That's a lie. This says to-do item class has already been created for you. I didn't create it. So.
Gee, thanks.
This is what I want you to create by tomorrow night, which you can. The to-do item's the easy part of it. From a high level, the UI, so what the user interacts with, right, user interface, they'll be able to create new items, edit items, delete, view all items, view specific items, delete items, click the program. The only place that you'll get extra credit this semester, right, is right here. You could save the list to a file and retrieve it from a file. So basically, if you think about it, a program runs, when it ends, all the data goes away. So you can add the functionality where you could save your list, come back and load your list, so the program keeps going. I have you write functions to do most of that, but I don't make you implement it in the UI. So
it would just be from the UI. You would do that, and then you would have that.
It would be a menu option.
Okay. Like with that.
But all that would be in the list. Pretty much all of these bullet points are functions in the to-do list. Okay? So it's not like you're recreating these. You're just being like, the UI is basically like, hey user, which of these items do you want to do? Oh, you chose one. Great. Give it the name of your item. Great. Now call the function, which we'll see in a second, that creates the item for you. Okay, so the UI is not, it's user interface, but it's not algorithmic anything. It's just call functions, call functions, call functions. Right? Use the stuff that you've already created, or you will create. I hope it makes sense. You should create the UI last. Agreed? Okay. The to-do list depends on to-do items. So the first thing you should write are to-do items. All right, and then move on to to-do list. Guess what? I gave you a unit test that will test the list and the items. Before you write the UI, I make sure those two things work perfectly. Because the UI depends on those things, and so you don't want those to be broken because then your UI won't work. So that's the UI. So even though, oh no, I have it in the right order. So to-do item comes first. That's what you want to do. So to-do item models information about a single to-do list item. So a to-do item has a description, right, underscore a priority, right, and a completed status. Right. Description, string, priority, and completed bool. Right? So this is the data that an item can store. It can store what is the description, right? Complete assignment 3. Right? What's the priority from 1 to 5? Right? 1 being highest priority, I think 5 being lowest priority. So you put that at what?
7.
Right, 7, yeah, exactly. You're gonna make sure it never becomes 7. Right? And then, is it completed yet? No. Right? You'll notice that you're going to write a constructor to set the parameters, or sorry, the data members. But I have some defaults, like if the user doesn't give you an integer, you default the priority to 1. If the user doesn't tell you if it's completed or not, you default it to false. Right, so there's some defaults, and we built constructors that had those defaults as well. You're going to write accessors and mutators for each data thing, right? So that's 3 accessors and 3 mutators. Most of them don't need error checking. but the priority one needs error checking that if they give you 7, that you set it to 5. Simplest thing, right? If priority is not 1 through 5, then priority equals 5. Right? Nothing too crazy. Agreed? And a couple functions. Right? One called toFile, which is basically like toString. But it returns a string containing the description, priority, and completed status separated by the @ symbol. So if my description was assignment 3, right, and my priority was 1, and my completed status was false, right, then my toFile would be assignment 3, right, @ symbol 1, @ symbol 0 for false. Okay. And we do that because that helps me separate, right? It lets me take a bunch of data and put it into a single string, which I can save to a file. And then if I can retrieve it from a file, I can be like, okay, great, create me a to-do item, right? To the first @ sign is my description. The next @ sign would be my priority. My next @ sign would be my completed status. Does that make sense? Remember that saving and retrieving is optional, right? So you don't have to do it. You have to write this function, but you don't have to do anything with that function. And then you have a member function called scrub, right? And scrub looks at your any string, although it's going to end up looking at your description, but it looks at any string, right? And replaces any @ signs with backticks. And we do that because if this was assignment 3, right, at midnight, because that's what time you guys like to do your assignments, right? Then my description has an @ sign, but the @ sign's already my delimiter in my toFile string. So I need to get rid of that so that it doesn't screw up how I parse it. And so it'll end up, right, changing that to a backtick to make things nice. And then that's it. Right? Yeah, that's it. Okay, why did I say to-do item is like you could do it pretty easily? No pointers, right? It's just what? 3 data things, right? With some accessors, some mutators, a constructor, right? And 2 simple functions. Simple-ish functions. Right? Everyone good with that? Right? It's not too complicated. Right? It's no more complicated than the temperature one that you had to make. Right? It probably is less complicated than the temperature one. The unit test will test your to-do item, make sure that you did it correctly. Questions there? So that's your to-do item. Note, if I say that your function is called toFile with a capital T and a capital F, that's what you should name it, right? You don't name it what I'm asking, right? This is the interface. You don't make your interface look like the interface I gave you, then my unit test won't work with it. Right? So you need to name them correctly. Questions there? Are you ready for the hard stuff? All right. Class to-do list is made up of to-do items, right? So this is your data manager class. So we have data, that's our to-do item, and then we need to organize our data, that's my to-do list. And let's talk about it, right? It contains a dynamic, look, I made it italicized. It contains a dynamic array of what? Dynamic to-do items, okay? Like create something dynamic, what do I need? New. And to get to it, I need a pointer. Agreed? So if I create a dynamic to-do item, right, and I have an array of dynamic to-do items, then technically what I have is something like this. So if its type is to-do item, then this array's type is what? Good. And then we know that arrays need what to them? Pointers. So if I have my list underscore variable, its type is what? You might want to take a picture of that before you leave today. Although I say, right, a pointer that can point to a dynamic array of to-do item stars. So the type of the pointer should be what? To-do item star star. You can name it whatever you want. I call it list underscore because it's a to-do list, right? And don't call it to-do list because that's the name of my class. So that's one of the data things. You also have a capacity variable and you have a size variable. Okay? And the constructor says creates a dynamic array of 25 elements and initializes the elements to null. So these all get initialized to null by default, right? These also need to get set. Okay, let's talk about the difference between capacity and size. Capacity is how many to-do items you can hold. Size is what? How many you are holding, right? So in my picture, capacity is what? In my picture. Yeah. It'll be 25 in your code. In my picture, it's 4. And what's my size? 1. Does that make sense? Right? So capacity is 4, size is 1. For you, capacity will be 25, and size will be? Yeah, but at the beginning, how many am I using? None, so 0, right? So in your constructor, you need to create this dynamic array of to-do pointers, set capacity to 25 and size to 0. Remember we talked about destructors last class, right? And so the destructor needs to delete all the to-do items and delete the dynamic to-do item array. Remember, every call to new needs a corresponding call to what? Delete. So if this was the thing I was destroying, I would need to delete this to-do item first, and then delete this to-do item array. That make sense? A little bit? All right, I'm trying to give you some cliff notes, but until you really get into it, you're gonna maybe not understand it all. Function 1, named add item, has one parameter, a dynamic instance of to-do item, meaning the parameter is a pointer to a to-do item, right? If there's room in the array, add the new dynamic instance to the first available spot. And I try to help you out. That's the current size. Meaning, if I had some pointer, I don't know why I made it big, some pointer to an item, right? And here was my dynamic to-do item, right? And if I said add that to my list, right? What would I do? I would find the first available spot. Well, the first available spot in my array is at location what? 1. What's the current size of my array? 1. Guess what? It's always going to be that. My array was of size 2. The first 2 spots would be taken up, and the first available spot would be at index location what? 2. This is where the right off by 1 actually benefits you. Because it's not off by 1. It's exactly what you want it to be. Right? And so it says, take the first available spot and point it to that dynamic thing. Right? My list bracket size equals item. Right? Make the pointers point to the same place. But it says if the array is full, increase capacity by 10 and then add the item. So this is the first time where your arrays can grow. Right? Usually we said, I'm full. Right? I can't take any more. All right. Remember I talked about that grow algorithm last class a little bit? I'll talk about it again on Monday. Okay? But we can expand it. All right. Function 2, delete item. An integer of the location to delete. I do say that the location is human readable. So location 1 is really index 0 because I just want to mess with you. All right. But after you delete the item, you will need to pack your array, shift all items down. Okay? What that means is that if I delete, right? If I delete this to-do item, I kind of have a hole in my array. And so I need to, from where I deleted, start moving this arrow to the next thing, the next arrow to the next thing, and then the last thing that was pointing to something, I need to make null. Right? Everything needs to shift. Okay? Lucky for me, I'm shifting arrows, which is a lot more efficient than shifting, right, items. So once again, the dynamices of, right, making my objects dynamic versus static, right, not dynamic, right, helps in my efficiency. And some error checking, right? If the location doesn't exist, just return null. Well, there's an easy one, get size, which just returns size. Get capacity, which just returns what? Capacity. They're like accessors for size and capacity. And hey, look, one called what? Sort. Right? So you need to sort the array by the priorities of the items. So 1 highest priority, 5 is lowest. So you can sort all your items, right, after they've been added, right? You can sort them by priority. Okay. Use whichever of the sorting algorithms that I give you that you like. Minus maybe selection because it's not stable. Right? I'm not going to grade you on whether your sort algorithm is efficient or not. Right? So you don't have to do a merge sort or a quick sort. You can just use a bubble sort. To file, right? Return a string containing all to-do items in the list. Basically, just call the to-do items to file, right, and put them one after another. Hey, we have some friends. So you should be able to output an overloaded, right? Or you should be able to output a to-do list with the insertion operator, and it should give you the list of all your to-do items. And then we have 2 private functions, one to increase capacity of the array and one to compact the array. So these are algorithms that I'll talk about next week. Because by next week, my expectation is that you just have to-do item done. Make sense? And then I don't even know, to-do UI doesn't really have much associated with it, right? So the to-do UI, we'll probably have an instance of C and reader and a dynamic instance of your to-do list. And then it will allocate your to-do list, it will delete the to-do list, and then really just has a function called menu that deals with your menu. Some of you have used C and reader before, some of you have not. It's just a way of basically error checking user input. Okay. Remember we did that lab, like lab 3 or 4, where we kind of wrote functions to deal with, well, let's convert strings to integers and strings to doubles and all that kind of stuff. It's all wrapped up in C and reader for you. With this lab or this assignment, I gave you all of the interface. So what does C and reader look like? I gave you slides and videos on how to use it. So we should be okay there. But you can always ask me as well. But just make sure, right, if you ask the user to enter menu item, right, and their numbers, you can make sure that they give you a number and it's between, let's say, 1 and 6 if those are the menu items. So that's for your UI. Remember, create your item first, create your list second, and create your menu last. Everyone good there? Okay, you have the rest of this week, next week, and the week after. So I'm kind of thinking, right, 1 of the classes per week, although your to-do list is definitely your hardest one by far. So we'll talk about some of the algorithms for the list next week, right, and go from there. Luckily for you, the labs for the next week are pretty easy. Today's lab's pretty easy. Next lab's pretty easy. I give you the pseudocode. You just have to convert the pseudocode to the actual code. Okay? Questions on any of that? You should be able to write the to-do item pretty quickly. All right? My unit test, unfortunately, tests the to-do item and the to-do list at the same time. Okay, so you may have to just stub out the to-do list, right, in order to run the unit test. Anyone know what I mean by stub out? Not comment it out, but create the interface, but don't write the definition. So to stub out a class, if I had class foo, right, if I had this class and I had some public functions, right, void f, int g, right, there's my interface, right, we can build that interface based off of, right, the PDF. To stub that out, I would just take all my functions, foo, void foo : f, right? To stub it, I need to make it a function, so I need to add curly braces to it, right? It's a void function, so I actually don't write anything in there. My g, which was int g, I would say int foo : g. Because it's an int, I would return basically whatever 0 is for an integer, which is 0. I say whatever 0 is, because if it was a string, you wouldn't return 0. you'd return like an empty string, right? Stubbing out a function and stubbing out a class allows you to just make sure that syntactically you have the structure down without worrying about any of the logic. Does that make sense? So in fact, I would stub out your to-do item and your to-do list and then compile it with the unit test. And it will make sure that you named everything exactly as I'm expecting you to name it. Once you have that, you have the structure down, and then you can start working on, okay, this function says to do this, what is the logic in order to write that function? That make sense? Okay, if you can get used to stubbing out functions, your life will get a lot better. Because there are a lot of functions that we are going to write and continue to write this semester. Trying to do all of them at once and then compiling it and trying to look at your long list of errors and fixing them is hard. Okay? Get the structure down, change, and then when it compiles, change one thing. If it doesn't compile, you know, right? I'm working on 2 lines of code. The problem's in those 2 lines of code. It's not anywhere else in the hundreds of lines of code that I wrote. Does that make sense? I don't know if you're going to believe me or listen to me, but it will make your life a lot easier if you can get used to stubbing out. Even in your labs, just stub it out, compile it, make sure you have the structure set up, right? They'll say you fail all the tests, right, because your array is not sorted, but it'll make sure that you, structurally set everything up so you don't have to worry about it. Okay?
Working in the real world where they say, here, you're doing these equations.
Yeah, right? It'll happen, right? Everyone has the interface, but right, I write function 1, you write function 2, someone else writes function 3. They all come back together, and that should all work.
Keyword should.
Should, yeah. I mean, we are human, and some of us are better than others. So.
Yes.
I think that's better than saying some of us are worse than others. I don't know. One makes me sound arrogant, the other one makes me sound like an ass. I wasn't saying I'm the one that's better. I'm just saying some people are better. Yes. Yes. All right. Get cracking on your lab. It shouldn't be too hard. Right? Remember when it says like 2, 1 or 2n-1, that means, right, 2n equal to it. Right? So a lot of times students screw up because they say like less than I, and they meant less than or equal to I. Right? You want to go all the way to that. Well, okay, so this one won't stop. So notice you start at n is the size of my array, right? I'm going from n to 1. So the decrement, right? So basically,
That's not a thing. It's not a, why are they using 3D arrays?
Because to sort an array, you have to do it more than one time. So this is my array. That's my array, right? And the bubble sort is really any of my sorts. I need to look at these 2 swaps. Look at these 2 swaps. Right? Before we can do that point. But then I'm going to go back and do it again. And so what happens is, because I am starting at size -1,
So this is a
basically making this
I had it
after I sort those values, I want to put
just
them
following just following
and so it's making my basically the outside sorted is saying I have an array that is sorted, but after I do it one time, part of the array is sorted. So it allows me to separate the sorted array. No, I would.
I mean, I guess you need
cut
to
it right down. Jay would say in that cut down.
Oh,
Cut it down. I said cut it down. I said cut it down. Because think of the I as basically just saying what is the size of the unsorted arrays. So the unsorted array is everything, and then once I bubble one time the last value sorted, So then it says the sort array is one less than, but keep subtracting from the size of the array for the.
So this one, this one?
This one?
Yeah.
So you said less than.
Yeah, so this
Yeah, well,
part needs to be right after this.
because we're going down.
Basically right after
For
this.
decrement,
Inside of
greater
this
than
board,
this would be
outside of this.
right? This would be I greater than. Yeah, because you know, so I starts as large. And we want to look at I is bigger than that large. The large value is bigger than 1, right? If it was less than 1,
it's going to be.
right, well, it starts large. If it wasn't even less than 1.
And then this one is flat, flat. And then I can't remember how to swap.
Is what right swap.
Basically, you see, you need to return the number of passes, which is effectively going to be J. You might consider incrementing a separate thing.
Incremented, like this is kind of like I going down, J going up.
Yeah, well, I guess what I'm saying is that you can't just use I or J, you can use J because it'll go away in second before the things, right? But you can create another thing outside this for loop, increment it inside the for loop, and then that's what you return. You see what I'm saying? So because you need to return.
So in your function, you just do that.
The number of passes that now does. So right now, the only thing that knows that is J, that goes away with the for loop. So if you create a variable that doesn't go away, it's still increments.
Like a variable outside,
Outside the for loop, yeah. I would do that, yeah.
So, right, but you have to.
And then, yeah, so that's what you're going to increment every time this occurs. Every time this becomes true. And you want to increment it, yeah, so you want to increment it and then.
This is just saying how I swap.
That's the.
Because if I have a swap, then
Effectively, that returns J, but J.
after this.
I would just put it right underneath the swap values, just to, pass.
So.
Oh, yeah, return pass.
So swap is the concept of this. If I have value X and I have value Y. Right, and I have 5 and I have 10. Right? Obviously we need to get them for that. But if I say X equals Y, then X will get 10 and I've lost 5. Right?
Right.
And so all you have to do is introduce the temp and then just put it in the right order. It doesn't really matter which order. But if you think of it this, if temp gets the value of X, right? So I'm gonna put a 1, that's the first thing that I did. Right, so now temp has the value of X, which means that X can now get overwritten because I have its value overwritten. So now Y can go into X, right? That's step 2. So X becomes 10. Does that make sense?
And then Y is equal to 10, so that gets it 5. Okay,
Good?
yeah,
Okay.
and then, for the swap equals true, do I need to create a value like a?
Remember it's pseudocode, so it's not assuming that your language has types or that's fine. So if the string is null, means that there actually isn't a dynamic string, then you do that, and then from there on out, that's why. So this is the final one, right? So the final word is that true, the word is found, that was false. So, right, so there actually is a find mode. which is why I said use the string function. And so the find function says you could say a string. Okay, a string. So it says my current dynamic string, I want to call the find function on it. I want to call this. And this says, talks about inbox. So this returns the location of where the word is located. It's -1, but and so we just basically because you can't be 0 because 0 is a valid spot. You can find the word at starting at location 0. That's the point. You can't. You need something that's an integer that's not. You need valid values. So you need that they also want to share valid values. That's what you need to for the string find the word. Or that might do that. Right? That means that you look for the word and you get equal string and probably read it down.
Value array, value 1 is on the root. If I do that,
like I can do this. Okay, so many characters are fine.
You're swapping is the array of J with the array of J.
okay.
That's what I swap. You just copy and paste it, you swap it.
Yeah, I guess I'm speaking too much on it, because I know that there's some values in there.
For me, the obvious thing is what's being passed out, right? You're only getting the array inside, so you're messing with the
Yeah, I was just looking at it on my thing on the error message that you know, font value.
Oh, yeah. Well, that's right, that's how it is.
That's why these are playing. So that's trying to help me out.
But then here's all this.
Whatever you pass into it gets translated to my loaded
And so 1 through 6, these are all of the overloaded functions that work with. You can call it a lot of different ways. We really care just about the first one. Anytime you see an ST, just think on that. So replace takes a position and it takes a length. Yeah, like it just comes right around. How many characters? So not how many characters you're going to put into it, but how many characters you're going to put. So I want to start at location 2, and I want to replace 3 characters. So we'll delete those 3 characters, and when you give it a string of 8 characters, we'll put those 8 characters for those 3 characters. And then you got it. You don't have to worry about it. It's actually, we'll do it for you. Yeah. So then, like, they try to give you the first example. So this would be like, so it says, I have some strings. Well, that's great. This is the attachment. So that's the string. It's going to say replace starting at location 9. Right, and then it's gonna part down. You know that in example is 1 about 3. Right, and so it started at location 9. Right, it's going to delete 5 characters. which is why it was, this is a test string, and now this is an example. So replace test space with in spaces. That makes sense? Yes. So what I'm going to do is basically finding on. You do that inside all the time. I find this inside of that. And remember, find returns the position of the string. Yes. Right? Yeah, right. So the nice thing is too, we just wrote find, right? This one up here, so you just do that, right? So it says replace, right? True if old rule is found and replaced, else return false. You can just do like if.
Say we have a sense of if we start out, and then go,
You just say that's right, you're looking for old word. That will return true if it found it, right? Otherwise it'll return false. Or I like to get all my error conditions out of the way. Yeah. Because then I can just write, okay, all my errors are good, so now I can just write code. So if the string is null, that's an error condition, throw comes null, right? If I wasn't able to find the word, right, then return false. Right? So at this point, I don't have to work on end pause because I know that the word exists. That makes sense? Yeah, that's clever. And then you basically have so instead of string dot replace, the name of my string is that string. And it's dynamic, so it's the string arrow. So replace takes three things, remember? Location to start replacing, how many characters to replace, and the string to replace. So this is good, right? You said best string 5, right? You're gonna find the old word. Right? So that will give you an integer that is the location where it found the old word. And you know it exists because we already did the if search. Right? So now we know where it exists, good, right? What do I want to replace? I'm going to replace the old word. So what is the old new word that I want to be? You want to replace all the characters that you do. Find the old word, where it starts, give me how many characters I want to replace, which is the length of the old word, right? And then the last parameter was what? I mean, it's got a function call inside of a function call.
Wouldn't it be start at I equals 0 and you go into it's not just a minus 0? Or can we start with the whole stack?
One of these, that one has a method. I'm not listening. Yeah, and then I would string start wrapping people in the strings. You would say, you said that you very That's because we're cooking it further. There's also like I'm sure. So what about CSCI?
I guess but it might be
basically the same. Remember the equals and overload operator, so there's a lot to do that. But really, public comments. Instead of all the stuff. So
This is
kind
kind
of use
of
string to call it the constructor.
Based on being running outside for this board. Alright, so inside of whatever further brace that is, but outside of this board. Something.
So it's kind of cool. So the default constructor for strings
Here
is
is responsive.
No, you do, no, let's see. Like this one, this further brace?
You can also create a
Down
string.
there. So right before that, it's right here, that's where you want your pass. Inside of that first one.
Most of the time what we create is actually.
Yeah. I believe that's right. That's what it says on here, it says it's defined as how many times the outside is, that's what it's saying.
So you can just say, I want to create a string of this character. So I did that a lot of times when I'm making.
The values put in the child value function now work and like first and see why because J wasn't there yet.
Sometimes I'll see on that, I just give myself a good little, like,
It's often not like you're not comparing like a void function to a boolean.
you can put
Yeah,
the, right, so this
this one,
says,
J wasn't declared.
or this says string constructor dash take another string.
But it's just, it's also not letting that. I'm comparing a void function to a boolean operator.
Oh, yeah, well, you don't need to, this just needs to be a variable that holds false, it doesn't have to be this whole thing.
Exactly.
Oh.
And then, when we delete pointers,
Yeah, you go.
so when we want to delete dynamic
And then,
things,
you don't need a whole swap line function.
you delete the pointer, it deletes the pointer.
Oh, what do you mean?
So it does.
The swap value thing, right?
So you delete the pointer, which actually isn't deleting the pointer, it's deleting
Well,
the.
I'm just looking at, this,
Yeah,
swap equals
it's like you, it looks like you turned it into instead of a for loop, and you go.
Right, which is why you said
I just
that.
kind of like following along with my pseudocode.
Yeah.
It could be as easy as number alpha and num coming in by reference. There's no guarantee on that. So when you say num plus plus and alpha plus plus, you might be like. It's fine.
Couple of examples after three.
Come around, come around.
Let's see, I know that they, I can declare, of course, that I.
And I and J. Pseudocode doesn't have to.
So that is what I think, yeah, alright, and then, what am I supposed to return here? I guess return the inch with the amount of loops it has.
Yeah, so all of these functions, you need to create a variable and count how many. So, problem sort says, return the number of passes the algorithm does. In this case, pass is defined as the number of times the outside loop runs. So you need to create a counter variable that starts at 0, and then inside the outside loop, you're using increment by 1, and then in the function O loop. So I want to count how many times the outside loop is running, which helps me make sure it's the counter. It's not too difficult. It will be okay.
I guess I just don't understand like the example for the software optimization. Swap equals false, I should have command, but use a swap values function. You can do this.
That's just a flag. That's just a boolean that we set to false.
So just create like a boolean variable and just.
Bool swap equals false, and then set it to true when you do it. But that should be down there and inside the loop, right, where you set swap values equals false. So replace that line. I like how you got like the loop of principle. That's what you're going for.
I didn't swap when it started, and it's the word.
Too much sense.
But I did.
When you're looking at levels of
Yeah, you don't have to use
Yeah, yeah.
I guess. Well, no, you need to. You don't need X and Y. X and Y are value.
did you say that?
Oh,
Yeah, that's. Yeah, that's what I was like, again, I did along things like equals and false.
You're just the same.
Variable. Well, no, you're actually. I got it.
I've been trying.
Sorry about that.
I just don't understand
You just like.
Well, this should be I side times 1. This should be I gradient. It would still work, but we like to be greater than or less than that. We would get into it. There you are. Is it working?
Oh, I'm trying to.
We'll try that. I can see. I know, we haven't ever translated pseudocode to code. A lost art. Yeah, sure. Which one? Well, which one looks like the outside one? Yeah, so in the outside one, we just say loop plus 1, right?
Yeah. Okay. Yeah.
And then outside of all of them, right? So basically the very last line of your function. Yeah.
Okay. But then.
So we have to play this one.
I don't know.
It shows the code input on 0, 4.
It's not you, but I think it's me.
So that probably would be your last function. Like, you know, that's what I normally go from. That one's good. That one's good.
Always start at the top.
Credit based hell, it's a terrible place to be.
Yes. That's why I just start at the top, because it makes me feel better on the inside that I'm right, I'm told. If not, I'm looking through a crap load code. Alright. Code does always happen. But usually it's somewhere within insert and the exit period list for the crap.
And then these warnings, it's a comparison between the signed and unsigned. The size is unsigned, so I and J should also be. You can write multiple ones if you want. My recommendation is write one, like give it default. You'll basically write multiple ones. Does it get errors or does it like lost the first pass maybe or something? We don't know yet. That would be my guess is that it lost it. Okay, with it.
Just like,
Oh, okay. It should work. Just check. Well, it's a little bit different.
You asked like 3 or 4 more.
yeah.
One thing.
It's the one that's held the sim.
Because double equals is a measure, that's just like you're comparing.
Did I say something that we both have
So there's 2 ways, so if you're assigning false to swap, you do single. If you're comparing swap to false, then it'd be double. You see what I'm saying? See the differences?
Oh, people are here.
Yes, but this is pseudocode. In reality, it's going to be 2 equals. If you're assigning false, you're comparing false.
But, this and this is single. Alright?
Yes. Yes. And then the if statement is going to be there, so. Correct, yeah.
And remember, it's not even say something.
Yeah, give me 1 second, see what
And now this one you're comparing it, so that it's like. Ooh, hey. Pretty good selection so far.
So instead of doing star dot, get rid of the star. And change the dot to 0. Because otherwise what happens is the star has a lower precedent. So it still tries to do the dot before the star. Yeah. Then the star to arrows. That would be right. Yeah, that's fine. It's there. This will all work.
Which is we did like, there's time on
They're just down actions. Hey, we did everything failed.
Yeah. Yay, what?
Oh, no, it's
Hold on.
talking about.
Hold on.
So
Hold that on.
the first for loop, effectively shortens the, length of the, and that's what this is. It's full length, it's been traded by 1.
Because
The one when you're,
it's not
small, that's when you're trimming it. Yeah, that's what this one is doing.
Okay.
Because you're setting high to the maximum bonus, and then you're trimming it. You're making it smaller.
So,
Yeah.
your bubble sort set.
Some of the first.
Mine starts at n minus 1, which is size minus 1. I goes greater than equal to 1.
Iterated by.
And I goes 0. Right? And your inside for loop says J starts at 0. And goes to I minus 1, so it should be less than I minus 1. And J.
Oh.
You
I
say
do believe
J is greater than the array at
Greater than eight.
You're good to 0 values. Greater than 0 is what
So I.
Oh. Yeah, they're the same thing.
I definitely scrubbed the algorithm.
Right.
So, for all the iterations that I is in
Not all of them, it's just gonna be for the first loop. You know, you have 2 for loops. The first loop is that way, the second one will stay that. The second one you want it to be smaller because you're going from 0 to big. This one you're going from big to small, so that's why it has to be bigger.
That's just, I meant like,
Oh.
yeah.
Anytime you're going from.
So your optimized bubble is probably the same, because it's the same, right? That's one value is I see 2 I's.
Oh.
So, I starts at size minus 1, I goes what? Right, what do you say?
Wow.
It was right up here.
Alive.
That'll be that.
Oh, this one's the wrong way too.
Try it again. not gonna work for us.
Oh, right.
That's what I mean.
Oh, that sounds more right.
So if you look at this, see this if statement, see how it's the same indentation as this for.
Yeah.
So it's not gonna, oh, that means, oh, you wrote yours.
So this needs to go back.
No, I'm saying that this for loop currently contains your if statement. The pseudocode says the if statement is not going to work. So this line code is not.
This is the perfect.
It's not going to work. So the loop starts here. Because you need to loop through the entire array. If you swap something, then you just swap it. Right? You say swap is true. You don't want to check false after the first thing, you want to check false after. All of them.
Yeah.
Otherwise, it'll stop before it. On selection. What do you think you did wrong on selection?
Why the same thing?
Well, let's see, that's one, no, that one's not.
Oh, yeah.
So, for loop, I had 0, I less than equal to size minus 1. Well, we had an up or down. Well, what do you think? Where did we stop?
Started low.
So which way we thought
Probably going up. And when this one will probably go down.
No.
Or, no. Oh,
They're not.
we're both.
Remember, it's fine then, so you find it on everything. Up one. Up one. Music says that. Alright, so now you're crashing it. Good job. Alright, so root plus small equals I, great. For j equals I plus 1. You say j is greater than equal to size minus 1? You said equal to. But what kind of what's there? What kind of up, so it should be less. Smaller than smallest. Okay. And then once again,
It's gonna be
on the outside.
outside. Only one.
That's that one. Right, that's business inside here. But right now, this is still inside. That's like real again. So these all say cash. And the way you read the algorithmic is that this is what I expect it to do. So I'm showing all the swaps basically.
Okay.
So I'm expecting it to swap 9 and 1, and then swap 9 and 5, and then swap 9 and 2, and then swap 9 and 7. That's basic 9 probably. And then you'll have to swap that all. And then yours says that you do all the same stuff again, right? So as long as those two things match, then algorithmically you did it correctly. Does that make sense?
Yeah.
So as long as those two match, algorithmically you did it correctly. Because once again, you could write bubble sort and it would pass optimized bubble sort and it would pass sort. They all sort, right?
Yeah.
And then your selection sort, right, it's basically the same. It's swap 9 and 1, 9 and 2, and 9 and 7, and yours say swap 9 and 1, 9 and 2, 9 and 7.
Okay.
Picture and patient.
Alright.
Because it's terrible.
So at first I define my function to be perfect, I get set this up, down, set it down, and then perfect that, and then now I'm still good. I use a bunch of fair identifiers, and just go all the way down.
That's fine. I'm just like that.
That is the ugly clear.
Okay, so that makes sense. So you define them here, right? Normally I can place them down below. So what happens is that swap values being declared, which go down this slide. So it's declared here. So it doesn't know about it until I get through.
So when I put it up here, I got that architecture x86, underscore 64, other stuff.
Really need to stop that. That's why it is. Define simple. Massage plane.
All right, Colin.
So those are just language that fine. All right, 13.
Yeah, that's the first one.
I guess they're.
This thing why does it pass the 11 until, I mean, yeah, pass the 11 until 12?
Because one I think is for a word that exists and one is for a word that doesn't exist. So there's that.
I think when I was reading this, it statement that,
Well, I think all of this. You're saying if the string I, which is a character, equals to an old word, which is a string. Right. Okay, here's very clear, right? So there is a function called recall, just like there's a function called find. So we can leverage that. I'll probably get satisfied. So we say if not find word. Looking for old word.
find word is broken.
But I did. No, I read the name of the function that we write. We're going to say return false. If I was not able to find the word that I'm trying to replace, then I'll return false, which is what this says. That's pretty clear, right? But what that means is that at this point, you have, exactly.
So then not do the or the
Well, no. We want to use a function called replace. Replace takes in an index. It takes in non-characters. And we do it all the way. So replace takes in, okay, where do I want to start replacing? How many characters do I want to replace? And what string of characters do I want to replace?
do I need this?
No. But how do we figure out where the old word is in the string?
You said no for.
No present. You did it for the
intermediate for you. This is how I'm used to doing it. I'm gonna go through this string time.
But that function, these functions do that for you. So the string arrow find, right, tells you where the word is located.
So the find function is basically. So that's for
Right, exactly. So here, the index is really the string arrow find. We're gonna find the old word. It says find the location of old word in this string. We know it exists because we already did a check up here. And then once I find it, I want to get rid of the old word, right? So how many characters is the old word? The cool thing about replace is that the number of characters doesn't have to change. I can replace 2 characters with 82.
So in this whole line of code, you're just using find to like traverse the whole.
So this finds where these characters basically exist in this string. And returns the index of where that stuff.
The string, you're pointing at replace with the function.
Yes.
And then in replace, you have to pass 3 bits. Then you're passing is using this string, you're gonna use the function find to find the old word.
Right.
Then
Which tells you where it exists. So
what index it is. So it's gonna be like I equals 4.
Right, yeah, exactly.
And then the old word outside is gonna be how long it is.
Yeah. So how many characters I want to use?
The word is 6 letters.
So starting at index 4, we're going to play 6 characters.
Oh.
And then the new word is what string of characters do we want to go in this place.
So why would you use this compass to do this?
Well, this size T tells you exactly. So it would just.
It's like what I did here was
Well, I mean, think about it, the loop just checks. Because the first one I looped found was whatever was supposed to be there. So found tells you the index of where the word is, or the return string and positive.
So the loop I did was basically do that.
Yeah, but once I get that first iteration, right, you get the
I just saw what I did this. I initialize J, create my second loop, and then I use diamond.
We'll make it 1 second.
Oh, yeah. Just been looking.
We're done. I'm done with you.
Okay, I just read that.
Okay.
Yeah,
So I think
I got the bubble part in the work.
2 labs did, I had to do the point H1 file here and add the header and add the end if whatever. And I had the epiphany last night that like, when I turned this 2 labs in, I only turned in the CCC and not the H. I did do the H, but I think I forgot. I don't know.
Exactly the same.
But if you do the get add dots, it'll add everything. So it should all be done together.
Say here, if swap false, break up.
If it's not, when I grade it, if I say it's missing, then it should all be done.
And then return to 0, which
I just, I don't know.
follow directions.
Yeah, sometimes it gets weird stuff.
Yeah.
It's supposed to be nice.
Well, if you grade it and you don't have it, I did do it.
Yeah, I know.
It wasn't hard.
If you already did it, you're gonna. Because if you return a 0, you're saying that it didn't pass.
Yeah, I literally have this I, find, it doesn't actually so I'm gonna go.
Yeah.
It's this, at that I, find another. So I don't even do this either, right? Because outside J,
Yeah, you get it.
Yeah,
right next to it. You'd be like, well, I wrote 10,000 lines of code.
I basically wrote just a bunch of.
And I
Why are you out of range?
It's gonna be like,
What do I do here?
Because I'm thinking that you have to capture the value of the pass when it stops swapping the value return. Right? Yeah. Because it has to do with that, right?
Right.
Yeah, it was.
If it's really unjust, it means that
That's
whoever
what I'm-
passes is.
Oh, okay, you're not using, you're not using.
And every time I try to find the sword, there's always a and that's all. Maybe you have to, maybe when it goes successfully swaps.
It looks exactly the same.
Oh, okay, because I'm not using the, because I'm not using the function.
Right, exactly.
Because when it swaps.
The function returns true or false, this is that's right.
Okay, yeah, this returns the position. Okay, gotcha.
Was that a zero?
Yeah.
They need zero.
It's because I didn't see
Just like, screw this dynamics now, let's just create a not dynamic.
And I just looked through the whole string and then if it was an alpha. Oh, it's an alpha.
So we know that you're not break theories for just.
They all look the same, right?
Because you're so used to it already.
You couldn't get the,
Okay.
Of course it did.
Yeah.
it was a left field.
So
I got young and a half working on understanding the bubble sword. Yeah, I'm telling you,
Okay.
what about the small sword? I'm telling you this one too. There's no, because no sword.
Or is it no?
One of them is a number of passes. I haven't really looked at the selection sword too much. I've just been trying to get a bubble sword to work. I've just been going back and forth between this and those.
Oh, no.
And I'm not seeing like any differences I have here that isn't in here.
So for,
Bro, I'm almost forgetting eyes. Kind of went straight.
yeah, well,
Yeah.
Because if I put it less than one and it was subtracting, it was like bringing out, it's calling the major fraction.
It says that for I equals size minus 1 and it goes to 1.
So it has to be less, there has to be greater than one.
Yeah.
That's it.
And then J is less than or equal to I minus one.
Yeah.
Yeah, that's it. But I still, no, I didn't agree. They're still going to it gets me mad that they start talking about science. Put satellites up on the mountain and do the what logic do you really swap out?
Yeah, I did. I did like this.
That's what I did too. That you do the exact same thing. Oh, wait, no, I put an if statement right there though.
Well,
No, you don't need that,
Make sure it's
because, I mean, yeah, I'm gonna remove these things. Because like this one.
I think the functionality thing I have is working, so.
because it's not even running because the if statement isn't true, so I'm gonna remove that.
I've been carrying this, and my problem was my code to, but it hasn't shipped some of this identical original.
I just went and deleted it and then rebuilt it. It's already no, I don't want to do it.
Because it's just been like copying stuff around and just making code for changes and not making much difference.
Ah, thanks. It looks dark in here. I'm trying to figure out why.
I'm just saying, you're thinking stuff.
Or here for programmers, right? So most programmers dark things all around, right?
So, one part of that. As is big, the parent, is.
Right here, you're equal.
Okay, and that's because this is the statement here. Right, so
Just normally it's inside of one, I would be 0.
So basically, when it looks at you, it says, should I swap or not? It doesn't just first, it's like, and then you.
Less than. Only if it's been there.
Okay, so let's say first swap first, you swap the very first two values, you still have 50 other values to check, but you said, oh, I did a swap. What you mean to say is after, right? After I've looked through all the values and performed all the swaps I need to swap, if I never swap, then I'm in.
Okay.
Does that make sense?
Yeah.
So you're just ending early.